So in this video, we're going to have a look at how to integrate trig functions that have sine and cosine or tangent and secant products. And so we're looking at these different combinations. Now we've looked at some combinations, but especially here we want to see what happens if our powers are even, if our powers are odd, what are we going to do? So let's start by looking at an example. Now in this example it says you want to evaluate the integral of cos cubed x dx. Now you may try the tools that you already have, like inspection. So you may try, okay, I'm going to see if I can use inspection, but it doesn't work because in order to use inspection you need to see a composite function and you need to see the derivative of the inner function. Now we can't see the derivative of cos x, which is negative sine x, so we can't use inspection. In the same way, we can't use u-substitution because u-substitution works on the same premise as inspection, that we let u be equal to our function, but then we get du to be the derivative. And again, we don't see that, so we can't use inspection and we can't use substitution. So now we need another tool. So in order to integrate powers of cosine, we can see here we would need an extra sine factor, sine x factor. Similarly, if this was a power of sine, we would require an extra cos x factor. So we need to see how can we introduce that. And in previous videos, we've looked at some similar examples, but now we're just going to make it a little bit more explicit. So here we can convert a cos squared x to an expression involving sine using this identity. So that's a very useful identity. So in other words, I can take that cos cubed x and I can split it up and make sure that I can see a cos squared x, and there's my extra cos x, so that I can substitute in place of cos squared x 1 minus sine squared x, which comes from rearranging that identity and making cos squared x the subject of the formula. Once I've done this, it's going to make my integral much easier to work with, which we can then use inspection preferably because I think it's a quicker method. Otherwise, you can use a u-substitution. So let's have a look how we can do that. All right, so remember that we are integrating. We're integrating cos cubed x with respect to x. We want to see a sine factor, so we're going to split up that cos cubed x into cos squared x, so we can use identity, times cos x with respect to x. Now we can replace that cos squared x with 1 minus sine squared x from our identity. Remember to keep it in brackets, because if you leave out the brackets, you're going to change the nature of the order of operations in the question. At this point, you can times into that bracket. So I'm going to times my cos x in. There we go. Times it in, and I'm going to get the integral of cos x minus cos x times sine squared x with respect to x. By all means, you could have gone straight to this next step. Remember that you can split an integral over a plus or a minus, only a plus or a minus. So it's the same as integrating cos x with respect to x. Remember your notation. You must have that dx there. Minus the integral of cos x times sine squared x with respect to x. Right, now we know from our table, let's actually just pop our table here so you can see. This one's nice and straightforward. The integral of cos x is just sine x. I'm going to pop that there. It's just sine x minus. Now remember, here we can use inspection because I see a composite function, sine squared x, and I see the derivative of the inner function. The derivative of sine x is cos x according to our table. So remember, we just use the power rule where we add 1 on and we divide by that. So it becomes sine cubed x divided by 3, which is the same as a third sine cubed x. You can write it over 3 instead if you want to, plus the constant of integration. Okay. So, in general, we try to write an integrand. Remember, the integrand is the function that's being integrated, involving powers of sine and cosine in a form where we have only one sine factor. We want to see that one sine factor, very important. And the remainder of the expression must be in terms of cosine, or only one cosine factor, but then the remainder of the expression must be in terms of sine. And this identity enables us to convert back and forth between even powers of sine and cosine. Let's have a look at another example. Example 2. This example says evaluate the integral of sine to the power of 5x times cos squared x dx. Now again, you can't use inspection because we don't have a function and its direct derivative. Okay, so there's my composite function. The derivative of cos x is negative sine x. But now I see sine to the power of 5x. Very different story. So what we can do in this case, very similar to the previous one, let's just write this out again. So I'm dealing with the integral of sine to the power of 5x times by cos squared x with respect to x. Very similar, but now obviously we've got sine and cos happening, and I'm going to generalize a rule after this example. But think logically, if I go to sine to the power of 5x, I can take out the sine x, so I get my nice little individual sine x, and then I'm left with sine to the power of 4x. Now that's an even power. So again, that's sine squared x, but it's been squared. So I can bring in the identity. So let's just see what that looks like. So I can write this as sine to the power of 4x, which is sine squared x squared, and I'm going to go straight there. Okay, so that is sine squared x squared. Okay, so that's sine to the power of 4x. There's my cos squared x, and there's my extra sine x. Remember, I'm going to want that extra sine x because I've got an even cos squared x. This gets replaced with the identity. So remember, the identity is sine squared x plus cos squared x is 1. So if I want to replace sine squared x as 1 minus cos squared x, remember to do that in brackets. So I've got 1 minus cos squared x. Remember that it's being squared. And I've got cos squared x. And I've got sine x with respect to x. Alright. Now here, it's going to take a little bit of work. These are quite long. You need to square this out because eventually, remember, we want to times things in so we can split up the integral. Can't times anything in until I've handled the square. So I need to square that. Remember your brackets. If I square binomial, I square the first term, so I get my 1 minus, and I double the product of the two terms. So it's 2 cos squared x. Square the last term plus cos to the power of 4x. And it's being multiplied by cos squared x and sine x with respect to x. Now your next step, which will always be your next step in these types of questions, is to multiply everything in. Now you've got to multiply to all three terms. So I'm going to take this whole thing here, that whole thing, and multiply it into all three terms. So let's do that. If I multiply it into all three terms, I'm going to have cos squared x sine x, because I multiplied by 1, then minus 2, cos squared x times cos squared x is cos to the power of 4x, times by my sine x, plus cos to the power of 4x times cos squared x is cos to the power of 6x, times sine x with respect to x. You don't have to show both of these steps, but I'm going to show them. That integral then gets split over that minus and that plus. So it's the same as the integral of cos squared x sine x with respect to x, minus, I can take my constant out, 2 times the integral of cos to the power of 4x sine x with respect to x. Let's see if we can squish this last one in, plus the integral of cos to the power of 6x sine x with respect to x. So you're going to handle each and every one of those, which you will do purely by inspection. But remember, when we do inspection, we just got to make sure that our signs are correct. And I'm actually going to use another color here for the signs. I'm going to use green, just to show you how they change. Here, this I can use inspection because I see a composite function, and the inner function is cos x. I need to see the derivative of that inner function. And if you go back to your table, let's pop the table here. If you go back to your table, the derivative of cos x is negative sine x. So I need to see a negative sine x, so I introduce that. I'm going to use green to do that. I introduce a negative, so I'm just going to use brackets to show you that I'm still timesing. But if I introduce a negative inside, I've got to introduce a negative outside. And let's do that with all of them. Here I'm going to integrate. I've got my power function, and I need to see the derivative of the inner function. The derivative of cos x is negative sine x. So again, I need to see a negative here. A negative, which makes that negative outside a positive. Here again, I need to see a negative sine x. So it makes that positive, negative. Right, now we can go about integrating. Just use the power rule where you add 1 to the power function, to the composite function, and then you divide. So don't forget your minus outside. It becomes cos cubed x over 3, which is the third, cos cubed x. Let's go to the next one. Don't forget that you've got a plus 2 there. That is cos to the power of 4x, so we add 1. Becomes cos to the power of 5x over 5. So I'm just going to pop my 5 there. The last one, we have cos to the power of 6x, so we add 1. So I've got minus cos to the power of 6x. We add 1, so it's 7 over 7, which we can write as 1 over 7. And don't forget, for an indefinite integral, to add your constant of integration. There we go. Right, so we've now had a look at how we can handle this, but let's generalize our rule. So let's look at our strategy for evaluating the integral of a product of a sine power and a cos power. Now, very important, if the power of cosine is odd. Now, I've used a lot of notation here, but you can learn it more theoretically so that you can then apply it in an example. But if we have a look here, the power of cosine is odd, so I'm going to make that power n 2k plus 1, because that's how we can write any odd number. 2 times something plus 1. Okay, so remember that. You're going to save one cosine factor. And then you use this identity to express the remaining factors in terms of sine. So you're going to replace the cos squareds with 1 minus sine squared of the angle. And this you can learn as a rule. So in the moment you see the power of cosine's odd, you save a cosine factor, and then you express the rest in terms of sine. So it looks like this notationally. There's your sine. Here's your cos to an odd power. So it's going to be cos squared x times k, because remember, if you had to simplify that, you're going to get cos to the 2kx. And here's your plus 1. Remember, when you times powers, you add the exponents. We do that so that we get the cos squared x, and we replace it with 1 minus sine squared x. And as we saw in the example, you times everything. You first square it or cube it, or whatever you need to do to it, then you times everything in and you use inspection. That's if the power of cosine is odd. If the power of sine is odd, then what you do is, instead of saving the cosine, you save the sine factor. And you use this identity to express the remaining factors in terms of cosine. So here, you're going to get your sine squared of an angle, and you express that in terms of the identity, you square or whatever, and you times everything in. Just a reminder, which we've done in previous videos, if the powers of both sine and cosine are even, you use the half angle formulae. Okay, so these are two of the formulae that we've dealt with, two of the identities, and sometimes it's helpful to use this one, which is another one of our identities rearranged. But that we looked at in more detail in another video. So that was with sine and cos. Now we can use a similar strategy to evaluate integrals that have tan and sec. That's because of their relationship with regard to their derivatives. So let's actually pop the table back here and you can see. Now the derivative of tan x is sec squared x. See, look in your table, the derivative of tan x is sec squared x. So we can separate a sec squared x factor and convert the remaining even power of secant to an expression involving tangent using that identity, because that's our relationship between sec and tan. Or the other way around, let's put the table up here. Since the derivative of sec, see, the derivative of sec is sec times tan, we can separate sec times tan factor and convert the remaining powers of tangent to secant. So it's that relationship because of their derivatives and because of the identity. So let's have a look at this example that involves tan and sec. I doubt you will see lots of these in a test or an exam, maybe as an extension question. Sine and cos is a bit more prevalent, but it follows the same principle, so we're going to have a look at it anyway. So let's see if we've got here, notice that the tan to the power of 6x, it's an even power, and this one's also an even power. Okay, so if we separate one sec squared x factor, we can express the remaining factor in terms of tangent using our identity. So this is going to be our really important identity. This then leads to an integral that we can do using inspection. Alternatively, you can use it, do it using u-substitution if you want to. So let's have a look using inspection. Here we're dealing with the integral, question again, of tan to the power of 6x times sec to the power of 4x with respect to x. Right, so we want to take out one of those sec squared x so that we can use the identity and get it in terms of tan. So I've got my integral of tan to the power of 6x. Now sec to the power of 4x is just sec squared x times sec squared x with respect to x. So what we do is we use our identity, which says sec squared x is equal to 1 plus tan squared x. So I'm going to change it to 1 plus tan squared x. And there's my other sec squared x with respect to x. Alright, so now we're going to multiply in. Now remember that needs to be multiplied in, and that needs to be multiplied in. Okay, to both of these, to the 1 and the tan squared x, to get two terms. So, it's the same as the integral of tan to the power of x, tan to the power of 6x. Now that's multiplied in, multiplied by 1. So I get tan to the power of 6x sec squared x plus, now I multiply that by the second term. So tan to the power of 6x times tan squared x is tan to the power of 8x, and I times it by sec squared x, and that's with respect to x. Now remember, we can split the integral over the plus. So this is the same as the integral of the first term. Notation is very important, remember. You add the integral of the second term. And now you can just use inspection. Because we can see here the derivative of tan x. Let's go back and just have a look here. Remember, the derivative of tan x is sec squared x. So to use inspection, we need to see a composite function. And then the inner function is tan x, and we need to see its derivative, which we do see. So the power rule says all I have to do is add 1 to this and divide by that number. So that becomes tan to the power of 7x over 7, which is the same as 1 over 7 tan to the power of 7x plus. Same thing here, there's the derivative of the inner function, so I go to the composite function and I just add 1, so it's tan to the power of 9x over 9, which is 1 over 9 tan to the power of 9x plus the constant of integration. Again, at the end I'm going to give you a strategy that always works, that you can learn, makes it a lot quicker to decide what to do. Let's look at one last example. Here we want to evaluate the integral of tan to the power of 5, and just steering away from x, just so we don't get too used to only using x's. Let's use theta, times sec to the power of 7 theta with respect to theta. Now, let's just explore this a bit. If we separate a sec squared theta factor, like we did in the previous example, we're left with sec to the power of 5 theta, which is not easily converted to a tangent because it's odd. However, if we separate sec theta times tan theta, so we take out one of those sec thetas, take out one of those tan thetas, we can convert the remaining power of tangent, because it's tan to the power of 4 theta, to an expression involving only secant using this identity. Tan squared theta, sec squared theta minus 1. So this then again leads to our integral that we can do using inspection. So let's see how that works out. Okay, so I've got the integral, let's write our question again, tan to the power of 5 theta times sec to the power of 7 theta with respect to theta. Alright, so we want to take out that one of the tans, one of the secs, so that we can then use our identity. So if I take out one of the tans, I'm left with tan to the 4 theta times sec to the 6 theta, take out one of those secs as well, and then I've got the sec theta times tan theta with respect to theta. Okay, so this is tan squared theta all squared, and I can replace tan squared theta with sec squared theta minus 1. So this is the same as sec squared theta minus 1 all squared. There's my sec to the power of 6 theta. There's my sec theta tan theta, which I want to leave there because I want to see that derivative later. Okay, again, we need to square this out, so I'm going to find the integral. We square that out, so it's sec to the power of 4 theta minus 2 sec squared theta plus 1 times by sec to the power of 6 theta times sec theta tan theta with respect to theta. Alright, everything gets times in again. All of that story gets times by all 3 terms. Okay, so these do get very long, especially in this case. Let's see if we can squeeze it in. So that becomes the integral. Sec to the power of 4 theta times sec to the power of 6 theta is sec to the power of 10 theta. And that's being times by sec theta tan theta. Then minus 2 sec squared theta times sec to the power of 6 theta is sec to the power of 8 theta. Times sec theta tan theta. Last one, plus, and we're timesing it by 1, so it's sec to the power of 6 theta. Sec theta tan theta. Just fitted it in with respect to theta. Split everything up, so it's the integral of each term. Let's do that quickly. Again, you could go straight here, or leave out this written step entirely if you like. Theta minus, take out your constant, second term, respect to theta, and I'm just going to put the other one underneath because I'm going to run out of space. The integral of sec to the power of 6 theta, sec theta tan theta, with respect to theta. Now for each of those integrals, you're going to use inspection. Remember, we can use inspection because here I see a composite function, sec to the power of 10 theta, and I see the derivative of the inner function, sec theta tan theta. So again, power rule says I just add 1 onto that exponent. So it becomes sec to the 11 theta over 11, which is the same as 1 over 11 sec to the power of 11 theta. Same thing here, but I've got a minus 2 first. I see the derivative of the inner function, so there I just add on 1 and divide by 9, so it's sec to the power of 9 theta. Plus, go to the last one, see there's the derivative of the inner function, so I'm using inspection, I just add 1 on. So I've got sec to the 7 theta divided by 7, so it's 1 over 7 sec to the power of 7 theta, and I add my constant of integration. So let's just end off with our general strategy for coping with products of tan and sec functions. Now notice, like in the first example, if the power of secant is even, so that power, that exponent there is 2 times something, so I'm going to call it 2k, just to generalize. K is bigger than 2, or equal to 2, because if it's not, that's not always going to work out. Okay, so save a factor of sec squared theta. We save that factor, so that we can replace it with 1 plus tan squared theta, so that the remaining factors can be expressed in terms of a tangent. Okay, so we make sure we have that sec squared theta. You'll see if you work this out, that becomes 2k minus 2 plus 2, which is 0, which gets us back to 2k, so you can check. The most important thing is that you take that sec squared x and you replace it with 1 plus tan squared x. Times everything in, integrate by inspection. Now, if the power of tangent is odd, you save, it's like the second example, you save a factor of sec times tan, and actually there I should have had x's. So let's just make this x's because I generalized this, took that from the example. And use that identity to express the remaining factors in terms of secant. So you make sure you get your tan squared, replace it with the identity, times everything in, and integrate by inspection. Now you might be thinking, what happens if they're both odd? What happens in other cases? Then the guidelines aren't as clear-cut. Sometimes we use identities, you can try integration by parts, and you might just need a little bit of ingenuity. But these really cover most of the extension type of questions you could actually get in an AP exam. Right, so this was just a way to cope with sine cos products and with tan sec products. Gives you another tool in your tool belt.